Adjacency matrix representation of graph. Adjacency matrix representation is a way of representing graph using two-dimensional matrix. This two-dimensional matrix, it will be of size V by V. And what is this V? V is the number of vertices in the graph. So what we'll do is, we'll first draw a graph and then try to construct adjacency matrix corresponding to this graph. So the thing is, coming to this topic of graphs, it is much easier to explain when we already have a graph beside, because we can easily explain from the graph that we have. So if this is my graph and I'm having these as the vertices, let us name these vertices as well. Let us call this A, this is B, this is C, and this is D. These are our vertices. So the next thing is, we want to form an adjacency matrix to represent this graph. We know there are total of 4 vertices, which means what should be the size of adjacency matrix? It should be 4 by 4 because there are 4 vertices. So what is a 4 by 4 matrix? A 4 by 4 matrix is a matrix in which there are 4 rows and 4 columns. That is when you call it a 4 by 4 matrix. The next question is, what are these 4 rows and 4 columns representing in this matrix? So the 4 rows, they correspond to 4 vertices that you have. So A, B, C and D. These 4 vertices are the ones corresponding to which you have 4 rows in this matrix. What about the 4 columns? They are also corresponding to the same 4 vertices. So why is it so? Because after this, each cell in the matrix, each of these cells, they will tell you whether there is a relationship between the particular pair of vertices or not. So for example, if there is a relationship between, let us say, some particular vertex I and a vertex j, then for this matrix of ij, this particular value, this will be 1. Whenever the entry in a matrix is 1, that means there is an edge between those 2 vertices. So in our example, from A, if you see there is an edge to B, similarly there is an edge to D, but there is no edge to C from A. That means you should put 1 in AB. So this is AB. Similarly, in AD also you have to put 1. AD, this cell is also 1. What about AA? AA will be 1 only if there is a self loop on A. So in this case, AA is 0, BB is also 0, CC is also 0 and DD is also 0, because in our particular graph, there is no self loop at all. Next thing, is there an edge between A and C? There is no edge here. Between A and C, there is no edge, which means in AC, we have to put 0 only. Because this is an undirected graph, if AC is 0, CA will also be 0. Similarly, if AB is 0, BA will also be 0. Why? Because in undirected graph, you don't have directions, which means AB and BA are the same. So here, because your AB is 1, here it is 1. So BA will also be 1. Similarly, AD is 1, which means DA will also be 1. So this is how it works. Similarly, your AC is 0. So CA will also be 0. What about this BC? There is no edge from B to C, which means BC should be 0. And what about CB? That should also be 0. What about BD? Yes, you have an edge from B to D, which means BD should be 1. DB should also be 1. Last remaining one is CD. What about CD? Yes, there is an edge from C to D. So CD should also be 1. DC should also be 1. So this is the adjacency matrix that represents this graph. So from this, few takeaways are, one thing is, for an unweighted graph, whatever we have done here, this is for an unweighted graph. So in case of unweighted graphs, whenever you have an edge between I and J, what will you do? Matrix of I, j, this will be made 1. And whenever there is no edge, you will make this 0. It is very simple. Next thing is, what if it is a weighted graph? So instead of unweighted, if you are having a weighted graph, in that case, these edges will be having some weights. So maybe the weight of BD is 2, weight of AD is 3, weight of AB is 4, and so on. Let us say this is of weight 3 only, CD. In this case, instead of simply putting 1, you should be putting whatever be the value of weight. So in this case, matrix of Ij will be equal to W, whatever be the weight, that is what you have to insert. So in our case, AD is 3 right now. So instead of 1, you should have 3 here. Will DA be also same? Yes, because it is undirected, AD and DA will always be same. Similarly, BD, there is an edge. So BD, you have 2. Similarly, this was DB. BD is also 2. What about AB? AB is 4. So BA will also be 4. What about this? DC? DC is 3. CD will also be 3. So this is for a weighted graph. Whenever you have a weighted graph, you have to put weight instead of 1. Next thing is, in a weighted graph, when you don't have an edge, you can put 0 if there are no edges which are 0 weighted. What happens is, in some cases, some graphs may have some edges which are having weight 0. So it can be any situation. It can be like cost of this edge is 0. Then you will put 0 here. So if in your case, graph is having 0 weight, then you can't use 0 to say that there is no edge, because you have 0 weighted graphs for which you have had 0 as the weight. So in that case, what you will normally do is, you will take a very large negative number or something that you don't want to use in the graph. You know that you won't use a number of this range in graph. So for that, that number is safe to use for something else. What will you do? In order to show that there is no edge at some point, for example, AC, there is no edge here. So because you can't use 0, what will you do? You will put some number, let us say minus infinity. This will show that there is no edge between these two vertices. So this is the case of weighted graph. Next thing is, what about directed and undirected graph? So if a graph is directed, let me just correct this to BD only. So it was 3. Okay, so in case of undirected graph, a speciality is Aij, okay, I'll write here, Aij, this will be equal to, A means the matrix, okay, M of Ji. Why is this? Because whenever the graph is undirected, the corresponding adjacency matrix will be symmetric. Symmetric, it's because AB is equal to BA in case of undirected graph. And what if it is a directed graph? Then you can't put this condition. AB need not be equal to BA. So matrix of Ij and matrix of Ji can be different if it is directed graph. So one more thing you should know is, what are the advantages of this adjacency matrix representation? Because in the next lecture, we'll be learning adjacency list representation. So first thing is, you should know when to represent a graph using adjacency matrix and when to represent using adjacency list. So that is the next thing you want to understand. When should you use adjacency matrix? So let us see in what situation adjacency matrix will give you advantage. It will give you advantage when, one is, whenever you want to check for an edge. If I want to simply check whether there is an edge between B and C, this particular operation of searching whether there is an edge between two vertices or not, this can be done in order of one time if you represent using adjacency matrix representation, because it is easy. You simply have to go to the matrix and check for, let us say BD is that you want to check for, then check for BD. So it is 2 is the value, which means the weight of BD, okay, it should have been 2, BD is 2. This is what it says. So finding whether an edge exists or not, or finding the weight of an edge, is an order of one time operation if you use adjacency matrix representation. So whenever you want quick access to all the edges, then you should use adjacency matrix representation. And the next thing is that adjacency matrix is generally suitable for dense graphs. So what is a dense graph? In a dense graph, you will have a lot of edges. So compared to the number of vertices, you will have good amount of edges. So if it is a dense graph, the reason why adjacency matrix representation is better is this representation will always take order of v square size irrespective of the number of edges you have. So whatever be the number of edges, this representation will always take space of order of v square because your matrix is v by v. So given that, even if you have an edge or if you don't have an edge, still the space is same, which means if you have a graph which is having a lot of edges, then it can make good use of this space. Otherwise what happens is most of these values will be zeros and you'll be simply wasting a lot of space. So that means you should generally use adjacency matrix, one, for dense graph, and secondly whenever you want easy access to all the graph elements. So this is where your adjacency matrix representation is efficient, and whenever the graph is sparse, that is there are very less edges compared to number of vertices, then this representation will be space inefficient.